going to be recorded and be made public record. So be very careful about what you put in the chat, and later on when we have an Q&A session, please keep in mind that it's going to be publicly available because we will upload this seminar online. Just a few administrative items. So Salva and I, we discussed this matter beforehand a few minutes before the seminar started. Salva prefers that all questions will be asked later on after he ends presenting. So feel free to leave questions until then. And we will have two modes of asking questions. First, you can at any time put a question in a chat, type your question and email. And later on, I will read it out loud and ask Salva, and he will provide his answer. And the second option is that you can, after the presentation ends, you can raise a hand. It's a special function on Zoom. You have to go to participants and click on the button called raise hand. I will see it on my screen. And when we get to the Q&A session, I'll give you a chance to answer those questions. So at this moment, I'm turning the mic to Salva. And Salva, please go ahead. There should be time for claps, but unfortunately, we cannot do it online. So the floor is all yours.
I caught myself.
Yeah, that's a good
so thanks, Yuri, for the nice introduction and also for the opportunity to give this online seminar. Yes, I think you cover a lot of things of my first slide, but just to mention that you have my website written there. So this presentation is uploaded. So in case you want to download it now and after the talk. And yes, what I'm going to talk today is about machine learning aid operational planning of power systems. So first, I don't know who is exactly joining this presentation, so I thought it would be nice to tell you a little bit more about where I am right now. So Málaga is a city in the south of Spain, and it's a very nice place. We have over 30 sun days per year, so actually this area is known as Costa del Sol. And the picture in the right is just the beach with some, typical food here in Málaga, where you put some fish on a stick and then you build them by the beach. We are not doing any of that, by the way, but so in the future, if you are around in Málaga, you should try those. But it's not only about sun and the beach. We also have a nice university that was established in 1972. And we have right now around 40,000 students and 2,500 faculty members. And there is also more and more technology companies setting here in Málaga. Actually, in the news sometimes you read that we are becoming the Silicon Valley of the south of Spain. As an example, we have the Andalusia Technology Park, including more like 600 companies with Huawei, Microsoft, IBM, 20,000 employees, and a turnover of 2,000 million euros. So, you have beach, but also you have some other stuff going on. I also wanted to take the opportunity to tell you a little bit about our research group. That's OASIS, and that acronym comes from Optimization Analytics for Sustainable Energy Systems. And that's basically what we do. So we apply optimization methods and data analysis to mainly energy systems. And that's what I'm going to talk to you about today. We are a very young group. We started in 2019. We are 6 members right now, but we are looking for 1 PhD and 1 postdoc. So if you also like the kind of things that we do and you like to apply, you can see all the information in the oasis.uma.es. So I guess people listening to this presentation come from different backgrounds. So I just wanted to set a little bit the scene by talking a little bit about power systems. So in power systems, we have some producers. And this is basically generating units producing electricity, like nuclear, like coal-based producers. Then we have some electricity consumers. It can be like factories, or it can be households. And then we have some lines so that the electricity can go from producers to consumers. That was basically the three main assets in power systems 20, 30 years ago. But in these recent years, we have new agents. We have more and more renewables, as you probably know, like wind and solar coming into play in power systems. And we also have some storage technology. Regarding decisions in power systems, we could split them in two main groups. You have long-term decisions. That means basically how much you are going to invest in producers, which kind of portfolio you want in the future, if you're having more or less renewables, if you need any update of the network. And that this kind of decision is for like maybe 20 years into the future. And then we have also short-term decisions. That means you already have all your assets built, and then you need to operate them. Basically, you have to decide how much each unit is going to generate. And then these problems are about power systems are usually very complex, because, for example, as I put here, the demand, the electricity demand is changing from hour to hour, is changing from weekday to weekends, is changing from winter to summer. So there is a very complex temporal dimension. And you also have to keep in mind that electricity is usually not produced in the same place where it's consumed. So you need some network to take electricity from one place to another. And then the spatial dimension is also important to take into account. Then the next slide is about the tools we use in our research group. So basically optimization, I guess you all know what optimization is, but you have a function and then you want to find the minimum of that function. That's a very short explanation of what optimization is. And we've been doing that for several years. And now we are becoming more interested in using machine learning tools. Like, for example, unsupervised learning, where you have data without any labels, and then you want to group data that are similar to each other, let's say. So that's basically the clustering. Then you have also supervised learning, where now you have labeled data, and then you want to find some kind of criteria so that if a new point arrives, so you can classify it as red or green in this example here. And finally, another kind of supervised learning is regression, where you are trying to find the relationship between two variables. So this is basically just a very short description of the tools we are using currently. In this presentation, I'm going to talk to you about two different applications of machine learning tools in power systems. And the first application is a long-term planning problem. We are going to focus in the temporal dimension, and then the machine learning we are using is clustering. And then in the second one, it's going to be a short-term operation problem. We're going to focus in spatial dimension, and we will use classification techniques. The first application is a joint work with Juanmi Gal-Morales. This is the title. It's chronological time period clustering for optimal capacity expansion planning with storage. And it was published in 2018 in Transactions on Power Systems. So you can go there and download the original paper in case you are interested, or if you want. What I'm doing here today is a very general presentation, so I'm not going very much into all mathematical details. But if you are interested, then you are welcome to download the paper. So what problem are we solving here? So it's going to be an expansion planning problem. So the horizon is just going to be 1 year. So for example, we are going to look into 2030. We are going to decide which investments we should do for that particular year. So the decisions are going to be the generation investment and also investment in the network. And our objective is to minimize the investment cost plus the production cost that will take place during that year in the future. We have, of course, some constraints, so we have to be sure that generation and demand are equal, like at every hour. We have some technical limits of units and also lines. The computational burden of these problems is high, because in 1 year a lot of things may happen to the power systems, right? So you have winter with some conditions, summer with others, and to make investments you need to take into account all possible conditions that may happen in the power systems. So how are these problems usually solved? Well, one way to do it is to take advantage of the fact that electricity demand, for example, has a very strong daily pattern. So as you can see here in the figure, these peaks are different days, right? And then they are very similar to each other. We have Monday, Tuesday, Wednesday, and then the weekend. So what you can do is use maybe clustering to kind of group days and then reduce the computational burden of your expansion problem. So what is clustering about? So I said a little bit about it. So basically you have a lot of data points without any label. What you are trying to do is to group the data that are similar enough to each other. So in this slide, we just have 3 different clusters containing points that are very close. How does this clustering apply to this expansion planning problem? So imagine that this is just a calendar year, and then all the red squares are days that are very similar to each other. And all the orange ones are also very similar, and so on. So in that case, you may just have to include in your problem the bold red, the bold orange, and so on. And then you go from a expansion problem with a lot of days to another that is smaller with only 4 representative days. So that's going to save you some computational time, of course, but then you have to keep in mind that if you do it like this, you are going to lose all day-to-day chronology information, because you are basically taking 4 days that are not consecutive. How do you do that? Each day you can characterize, for example, by 24 demand values. This is just normalized values, 24 wind values, and 24 solar values. And this is X2 is a different day. And then you can decide if these 2 days are similar enough or not. Use it just, for example, norm 2. This is a very straightforward way to do it. So let's say we have 2 weeks, so we have 14 days, and then you have to reduce that to only 2 days. So you start with, we are going to apply a hierarchical clustering technique. You will start with 14 clusters, so each day is 1 cluster. Then we determine the cluster centroid, so that's, since we only have 1 element, that's just the element we have. We compute the similarity between different clusters. You can do that in different ways. Here we use the ward distance. And then you merge the 2 closest days. So let's say we have 14 days. So let's say that Monday of the first week and Monday of the second week are very, very close to each other. Then you merge them, and then you only have 13 days. And then you go on until you end up with only like 2 representative days. Of course, the weight of each representative day is going to be proportional to the elements within the cluster. So in case this was not clear enough, if we have here a figure using the data I showed you before about electricity consumption, where we only use 2 2 representative days. So the initial number of days is 14 and we go to 2. You can see here, this is one representative day and this is another representative day. And then it seems that this approximation is not good enough, I would say. And you have reduced significantly the problem from going to 14 to 2 days. What's the problem now? As I told you at the beginning, in power systems, we are having more and more renewables and storage. And then we were wondering if this representative date technique is going to also be valid for new power systems. Well, of course, we have a renewable generation because it's free and reduce emissions. But the thing is that renewables can generate electricity at the wrong time. And then storage is like the perfect partner for them, because if the wind blows, for example, if the demand is low, we can storage energy in the battery. And if the wind doesn't blow and demand is high, then we can take the energy from the battery. So the bad thing about renewable, well, one of them is that, for example, wind doesn't have a very strong daily pattern. So this is a real wind production in Denmark for the first 2 weeks of 2016, I think. So it's not like electricity demand, right? Where we have these very like strong patterns. So if you use the representative days approach and you also choose 2 representative days, you can see that the approximation is not that good anymore. So you see the 2 days are, here is 1 and here is the other one, right? And then you just have to use one or the other to replicate the original data in red. That's one thing that is bad about representative days, but there is a second bad thing. And this is related to seasonal storage. So a storage, you can, for example, use it to move energy from day to night, or you can use it also to move energy from Monday to Friday. And that's what's called a seasonal storage, where you have like several days in between. And this is very crucial to overcome dark periods in Central Europe, where you may have 3 or 4 days in a row with clouds and no wind. And then this seasonal storage that can alleviate that situation cannot be modeled using the representative days approach, because if you remember, all the day-to-day chronology is lost. So what we thought is, what if we propose a new clustering technique that is going just to group consecutive hours. In that way, we do 2 things. First, we can better capture the dynamics of wind and other renewables. And then we can also, we are going to better keep track of chronology. And then we can model more accurately storage devices. So it's pretty similar to the other approach. If you think about it, we are just taking 2 hours. So now each hour is characterized by a demand value of wind and solar, for example. And then the similarity between 2 consecutive hours can be computed as the 2 norm, for example. Then what you do, again, we are going to use 2 weeks, so that's 336 hours. So that's the initial number of clusters. So each hour is just 1 cluster. We determine the centroid as before. We compute this similarity between consecutive hour, and this is the step number 4, is the most important one, where we just merge the 2 closest adjacent clusters. So maybe like 4 p.m. is very similar to 9 p.m., but you cannot merge them because they are not consecutive hours. You can merge 4 p.m. either with 5 p.m. or 3 p.m. And then you go on until you reduce the number of clusters, and then the time duration of each aggregated time period is going to be proportional to the number of elements in the clusters. So let's try that with the wind data I showed you before. And as you can see, at least visually, the approximation seems to be much better, right? And then all chronology is kept, so you can also model storage in a better way. So, and that's going to help you to make better investment decisions. That's the whole point of this work. So we tried this in a kind of realistic electricity network based on the European system, where we had 28 countries. We were looking at the year 2030. We could do investment in conventional generation, renewable, transmission, and then two storage technologies. The intraday, remember, to move electricity from day to night, and interday to move electricity from Monday to Friday. We assume a greenfield approach with no initial capacities, and then we also had a target renewable penetration that we had to meet in year 2030. This is just some data we use. So we have, this is the investment cost. So for example, base units have a very high investment cost, but then the production cost is low. And we also have some ramping limits, meaning that you cannot change production drastically from 1 hour to the next one. Then we have a peak units that the investment costs are lower, but then production costs are higher, and you don't have any ramp limit. We have wind and solar, and then the two storages. The intraday has energy capacity of 6 hours. This means if you have your battery empty, as you start charging it full rate, then it's going to take 6 hours to be completely full. And then this is not so too high, 6 hours, and that's why you normally could use this storage to move electricity from day to night. And then in the interday, the energy capacity is 48 hours, so this is more suitable to move to store electricity for several days. And so what we are going to do with the results is to compare two things, like business as usual, then the different clustering. So on the left part of the slide, you see we have original data. Then you can solve the full problem. That's going to be very computationally expensive. You will obtain the exact investment. Then you fix those investments, and then you run a whole year simulation, considering all the 8,700 hours in the year. And then you get the exact results. On the right part, you take this original data and then you cluster the data. You solve a simplified problem, and that's going to be faster than the original one. Of course, the investments are not going to be exact, so there's going to be some degrees of approximation. You also fix these investments, and then you again run the year simulation, including all the hours, and then you get approximate results. We're going to compare 4 different methods. The full year is just business as usual. Then we have 28 representative days. So that's going to be called D28 for representative weeks. So it's the same story, but instead of grouping days that are similar to each other, you group weeks. So in somehow you are also trying to keep a little bit better chronology. And then we have the proposed approach with 672 period. So if you do the math, then the total number of hours that you are going to consider in these 3 approximate methods is the same, and therefore they are going to have a similar computational burden. So this is the results. So there is a lot of information, but I'll take you through it. So on the left, we have investment in base, peak, wind, solar, hydro, and intraday, interday, and network. These are all aggregated values for whole Europe in 2030. And then you have total costs, including investment and production cost, the share of renewables, and the loss sharing. And then each column belongs to each of the methods we are comparing, and we have a renewable target of 50%. So let's see some interesting remarks about these results. So first, the full model is meeting the renewable target of 50% at the lowest cost and with no loss shed. But the problem is that you need a lot of computational effort to solve it. If you see that there is some kind of, it's investing in both intraday and interday. So this is already telling us that there is some value on this seasonal storage I was talking to you at the beginning. Then if we go with the representative week approach, it's interesting that there is no investment in peak generation, and that's basically because if you can only choose 4 weeks in a whole year, you are probably going to miss the day with the highest demand, and then you don't invest a lot in peak. But then when you run the whole year simulation, you're going to have a lot of loss shedding, and then the costs are very high. In the case of the 28 representative days, it's also interesting that there is no investment at all in this interday storage. Why? Well, if you only have, if your each element is just 1 day, then it doesn't make sense to invest in a storage that is meant to move electricity from Monday to Friday. And this is all due to the fact that all day-to-day chronology is lost. Neither of these two approaches, the representative days or the weeks, is meeting the target. So you do the investment thinking you're going to meet the 15% renewable target, but then when you go actually to 2030 and make operating decisions, then you are unable to meet that target. So I think that's also important. And finally, the proposed approach, the chronological clustering, is approximating quite well the wind, solar, and storage investment if we compare it to the benchmark. And also the cost and share of renewables is almost equal to the benchmark, and the loss share is very low. So that seems a good thing. The results I showed you before is just for one renewable share, this 50%. Here you have on the left the cost and on the right the loss shedding. But we also run the simulation for different shares. So the important thing here is that if the renewable share is very low, like around 30-35%, then actually the differences between the chronological and the representative days approach is not that high. But as you go to the right, then these differences are more significant. So in the next slide, what we had is somehow the average cost for different renewable shares, and then we compare it to the full model. So the increase of in average for all targets for the representative days is 13%, the representative weeks around 48%, and the chronological only 6%. So this is half of the representative days. And the computational time of these three approximating methods are very similar to each other and way below the benchmark. And finally, for these examples, we took 672 periods, but you can also increase that. And here is the evolution of the increase of the cost and also the computational time. So as you can see, the red dots belongs to the proposed method, and the other two to representative days and weeks. So for any number of time period that you choose, it seems that our method is working better than the others. And of course, if you choose 2,500 time periods, then the computational time saves are not going to be very high. But also on the right, you can see that the computational effort of the three methods are of the same order of magnitude. And finally, this we wanted to know if this work always, and that's not the case. So these numbers are in the base scenario is just the number I showed you before, and then we wanted to also compare this method in the case in which we only have wind or we only have solar. So if we only have wind, it's this method performs better, but we only have solar, that's not the case. So the representative base is a better approach. And this is basically because if you only have, if your renewables is only coming from the sun, that also has a very strong daily pattern, then you're not interested in seasonal storage. You just want to move electricity from day to night, and then the representative base is not a bad choice. So just to go into the conclusions, what we talk about is about how the origin of this study is that we think that existing approaches do not capture very well midterm dynamics, and also doesn't model properly storage devices. And then we propose a time period clustering that is trying to improve these two things. And the key point here is that our method allows us to see the economic value of pairing seasonal storage with renewable without a very strong daily pattern. So that's the key advantage of the clustering method we are proposing. Yeah, so that was the first part of the presentation. And now we go to the second one. So we have a little bit to change our mindset because we are going from so we did until now was a long-term planning decisions, and we are going to move to a short-term operation problem where we are going to focus in the spatial dimension, and the technique is going to be classification instead of this clustering. This work is the title is data-driven screening of network constraints for unit commitment, and it's a joint work also with Juan Miguel Morales and Asunción Jiménez Cordero. And this was accepted in Transaction Power Systems around 2 months ago, but it's already available online in case you are interested. So the problem we are solving now is a unit commitment problem that maybe you are familiar with. The time horizon is reduced to just 1 day, and the decisions are generation commitments. So basically, which units are going to be on or off. The generation dispatch, so how much these units are generating, and then the power flows. Our objective is going to be to minimize the production costs, and the constraints are similar to the previous problem. We have to meet, we have to make generation equals demand, and we have some technical limits of generating units and transmission line. And the computational burden of this problem, even though the time horizon is just 1 day, is also very high. And the reason is that we have binary variables. Mathematically, you can formulate a unit commitment problem in a very generic way, like this, where you have an objective function, and then we have continuous variable x, and these represent dispatches and power flows. And then we have binary variables y, and these are the status of the units. We have an objective function minimizing the costs, and then 1b is the technical constraints of the generating units, and 1c is the constraints of the network. So even though f, g, and h are all linear, this problem is NP-hard because we have these binary variables, and then this problem scales very badly. So to tell you a little bit more about this research, I need to explain you some classification about constraints that we need. So let's say we have this optimization problem in which we have one continuous variable and one integer variable. We are maximizing the sum of both of them. So if you look at the figure, what we want is to be as up and as right as possible. And then we have 4 constraints that are also plotted here in the figure. So since y is an integer variable, the only feasible points are the blue lines here. And since we want to be as up and right as possible, A is the optimal of this optimization problem. And based on this optimum, we're going to classify the 4 different constraints. So constraint to B is an active constraint because it's binding, and if you remove that constraint, then the optimum is going to change. Indeed, the problem becomes unbounded. So this is going to be an active constraint. Then we have an inactive constraint, that's 2C down here, because if you remove it, then then the optimum it doesn't change for this particular objective function. Since we want to be as up and right as possible, removing 2C is not really changing anything. But if you had a different objective function, that might not be the case. But for this one, we can remove it. So that's going to be an inactive constraint. Then we have 2D, and this is a redundant constraint. And that you can remove for any possible objective function, unlike the inactive constraint. So as you see here, like the 2D is y lower equal than 4.5, and then 2E is y lower equal than 3.5. So it's more or less clear that 2D is a redundant constraint. And then the last one, that's 2E, that we have defined these constraints as quasi-active constraints because they are not binding. So you have some slack here, but if you remove it, then the optimum is going from A to B. So it's not binding, but then you cannot remove it. So it's something in between, and we define them as quasi-active constraints. So let's go now to the actual unit commitment problem. It's a very simple modeling, but it's enough to show what our method does. We are considering a single period problem with linearized power flow equations. We have thermal units, renewable units. We assume non-demand, so no stochasticity, and we don't have any failures. And so probably you're familiar with this formulation. The L is just a penalty on the balance equation at each bus. And you have 3D is the generating constraints, and then 3E is the transmission line constraints. So this A parameter is the power, the PTDF, and this PTDF tells you the impact of injecting 1 megawatt in one bus, how that affects the flows through a given line. And then we have our binary variables. So the whole point of this presentation is to compare 4 different methods to remove constraint 3E. And if we remove them, like hopefully we will reduce the computational burden of this problem. So it's going to be 8 methods. I know it's a lot, but most of them are very intuitive. So I hope it's clear enough. So first we have the benchmark method, and that's business as usual. So no network constraints are removed. The computational burden is going to be very high, but it's useful to compare with. Then we have the single bus method, and this is completely the opposite. So we remove all constraints. It's going to be very fast. It's going to give you good enough solutions if your power system is not very congested, but then it's going to be highly suboptimal if in any other case. Then we have the perfect information method. This is a little bit, it's not very intuitive. It's going to remove all constraints not binding at the optimum. So you cannot really implement it in practice because you don't know the constraints that are binding if you haven't solved the problem. And that's the whole point. But it's going to be useful also for comparison purposes. And then in the example I was showing you before, this one here, so this method is going to remove 2C, 2E, and 2D. So it's going to remove all of them except 2B. And that's going to change the optimum. So even though you know in advance which constraints are going to be binding, then you cannot remove the rest. That's going to give you suboptimal solutions. Then we have the naive method. This is also very intuitive. It's just going to remove all line constraints that have not been congested in the past. So you have some historical data, and then line 36 have never been congested. So I guess it is going to be congested in the future. And this is going probably to remove a very low number of constraints. Then we have the constraint generation method. This is also quite intuitive. So you start with solving the unit commitment without any constraint. Then you compute the power flows. And then if you see a power flow that is above line capacity, then you include that constraint. And then you solve the unit commitment again, and then you iterate. So since you have to solve a unit commitment problem at each iteration, it's going to take a very long time. Then the roll method, this is one of the existing methods in the literature to remove constraints, these network constraints. So what you have to do is for each line in the system, you have to solve an optimization problem that this is doing is maximizing the flow through a given line. So let's say that all generating units are agreeing or producing what is needed to maximize the flow through a given line. If you solve this problem for a line and then you actually reach the maximum, then this capacity line constraint is kept, because there exists a possibility that that's going to be congested in real operation. Even if all units are pointing to congest a line, but it doesn't get congested, then you can remove it safely. And this method is only going to remove redundant constraints. And then we have the method we proposed in this work, in which we are going to infer the line congestion through statistical learning. So one advantage it does is that you don't need additional optimization problems. It's not only going to remove redundant, but also inactive constraints. The method we use is a classification method. It's just the nearest neighbor, because it's very simple and easy to understand. So this is how it works. You have some net demand. This d tilde is a vector of net demands for the whole network for different hours in the past, and SLT is the status of the line, meaning if it's 1 if it's congested and 0 if otherwise. Then a new time period comes, and then what you first do is to find the closest neighbors. And you can do that by just this distance that we propose, in which this is just norm 2 of the difference between net demands. But we are multiplying this, we are weighting the demands with the PTDF. In that way, 2 individuals are going to be close if the net demand of those buses that have a higher impact on the power flow of that line are similar enough. So maybe if you have line 32, you don't really care about what happened in bus 95, because it's very far away. So you want to focus on the buses that are nearby that line, let's say. If the line was uncongested for all the neighbors, then we can safely remove that constraint. Otherwise, we keep it. Maybe this figure helps you to understand the intuition behind the method. So this is a lot of, you can see that a lot of hours, operating hours. And then in the red squares means that the line is congested. The blue one, they are not congested. And then a new time period arrives. That's the black square. Then we take the 5 closest neighbors. And even though there is 3 cases in which the line was not congested, we have some in which it was congested, and I am very risky. So I'm going to say that the prediction is that the lines, it may be congested, so I better keep that constraint. And finally, we have a combination of the data-driven and the constraint generation. So first, we just run the data-driven, as I explained you before. And then if we see that some power flow is above the limit, then we include that constraint iteratively. We have tried this method in an IEEE test system with 19 wind farms. It has 120 transmission lines. We have 300 training days and then 60 test days. And we also consider a low and high congested case, and I'll explain why in a minute. We are doing a comparison very similar to before. In the left-hand side, you have the business as usual. So you have the regional network. You saw the benchmark model that's going to be computationally expensive. You have the exact commitments. You run the simulation fixing the commitment, and then you get exact results. On the right-hand side, we are going to screen some constraints and remove some of them and have a reduced problem that is going to give you approximated commitments. Then we fix those commitments, and then we run the whole simulation again, and then we have some approximation results that we compare with the exact ones. So again, there is a lot of information here, but let's go through it. We have here is just the 8 methods, just as a recap. Benchmark method is business as usual. Single, you remove everything. Perfect, you know beforehand the constraints that are binding. The naive, if a line is not congested in the past, it's not congested in the future. Constraint generation, you iteratively add constraints that are violated. Role, you have to solve this optimization problem to push towards each line. Data-driven is our learning method. And then the last one is a combination of the data-driven and the constraint generation. This is the low congested case. So you have 5-line road here. The first column is the number of constraints that are removed. The second column is the error in the cost, and the third one is the infeasibilities that it may happen because you have, remember, like approximated commitment that actually may be a little bit infeasible. And then the last one is the time as a percentage of the time of the benchmark. So let's see some interesting facts. The first one is that the single man method is good enough, and this is because you have a very low congested system. So removing every single constraint is not that bad. Then we have 5 methods out of 8 are finding the exact same solution at the benchmark. And I'm saying this because in some papers in the literature doing this network screening, they just provide results for low congested systems. Then it's not very difficult to do it right in that case. So just so you are aware of this. Roll method is very conservative. You can see that all the other methods are removing above 99% of the constraints, but roll method is only removing is 85, so it's keeping like 14% of the constraints. And then the naive and the data-driven, so these are the 2 methods that rely on some historical data, are the one that achieve the highest time reduction. So let's go to a more interesting case. So this is a high congested case. So what we have done is just reduce the capacity of the lines. First, the single bus method is not any good now. And the results, it's very fast, but you have the deviation from the original solutions are huge. And even the perfect information method is giving you bad results. And this is, as we discussed before, because you are removing quasi-active constraints. And then we have the constraint generation. It's removing a lot of constraints, so 83% of the constraints are removed. We get the same solution as the original method, but the time reduction is not very remarkable. So it's only 65% of the benchmark method. And the roll method is only removing 22% of the constraints, and then also the time reduction are not very impressive. Finally, our data-driven method is removing almost 90% of constraints at the expense of having some 0.1 infeasibility. But the reduction of the time is it's 12%. And then finally, if you are very worried about these small infeasibilities of the purely data-driven model, as I said, you can combine it with constraint generation, and then these infeasibilities are taken away at the expense of course, increasing a little bit the computational time, because you have to increase to do some iterations. And finally, while comparing the computational times with small systems is sometimes a little bit tricky. So we decided to do also a large, more realistic size system. And these are the results. So as you can see, the computational time of the data-driven method that we propose is similar to the single bus and the perfect information method, but the errors that these methods involve are much lower. So this is 0.04% error in the cost and 0.03% in physical cases. But as I said before, if you are interested in recovering the exact solution as the original problem, you can combine it with the constraint generation method and increase a little bit computational time. So the main takeaway of this slide is that our conclusions are also valid for realistic power systems. So this is just a summary of all methods. Here is just the number of remove constraints, and red means that you are not taking away any constraint. And the orange are the two methods that are a little bit conservative, and they don't remove a huge number of constraints. And the second column is the ability to actually find the same solution that the benchmark. So in red, these methods are very bad at this. And we have the three methods, the constraint generation, the rolled, and the data-driven plus constraint generation, that are able to recover exactly the same solution than the benchmark. And then this is some intuition about the time. So for constraint generation, although these the savings are not that impressive for different reasons. For constraint generation, because you have to iterate a lot, and each iteration you have to solve the unit commitment. And for the roll method, because you are very conservative and not a lot of constraints are actually removed. The combination of this data-driven and constraint generation seems like a good trade-off between all these things. Yeah, so this is the last slide of my presentation. So the main idea of this work is that if we remove some capacity constraints of the unit commitment problem, we're going to reduce the computational burden. We propose a data-driven method that it relies on access to historical data, but on the other hand, it can remove both redundant and inactive constraints. By doing that, we achieve computational savings that range from 70 to 98%, depending on the congestion of the level of the system and the size. And this method also may involve small infeasibility, but that can be taken away by combining it with constraint generation method. And yeah, so that was all I had for you today. This is the OASIS website again, and my email in case you have questions or comments or anything. These are more than welcome.
Thank you. Thank you so much, Salva, for your presentation, for your talk. Thank you for taking the time. There should be a place for a lot of claps, but again, we cannot deliver it, unfortunately. So please trust our word that we want to do it. And right now, I want to open the mic for the questions. And there are two ways, as I said. One way is that you drop a question in the chat, and the other one, you raise a hand on Zoom, and I will unmute you. So far, we have one question. Go ahead, Jim.
Hi, Salvador. Thank you so much for the nice presentation. I have a couple of questions about actually both parts in your presentation.
Okay.
Yeah, first of all, I'd like to hear more about in your result of the simulation, the proposed approach shows almost zero error or infeasibility, right? So is it coming from the fact that when you do this k-nearest thing, do you determine whether it's congested or not in a conservative manner, so that, for example, if there is any say red circle in your boundary, then you decide your new set is congested?
I don't think so, because being conservative is in your favor. To be infeasible. I mean, it's not in your favor to reduce computational time, but it's in your favor to keep your solution feasible. In the sense that if you are infeasible, it's because you are removing a constraint that you shouldn't have. You know what I mean?
Yeah. So in your
so being conservative is in favor of being feasible.
Yeah, so what I'm asking is, in your illustration, say there were 5 dots and 3 were blue or 2 are red or something like that, right? And you determine that your new set is congested based on the portion of the congested line. Is that correct?
No, if there is only one vote saying that the line is congested, then you keep the constraint.
Oh, so even if there's only one line is congested, then you determine it as a congested, and then you include that constraint. So,
yes.
All right. So I thought that was quite a conservative manner, because
it is.
Okay. All right.
I mean, you could, we changed that, but let's say relaxing this criteria a bit, it didn't help. So it works. The computational savings were not better, but we have more infeasibility. So that's why we kept it like this.
All right, thanks so much. So my second question is about the CPU time. The computational time you showed me is, I believe it's a summation of the clustering computation and the solving of actual optimization, right?
Yeah, you mean in this problem as well?
Yeah, the part. Yeah, so what I'm curious is about so for example, in the last row you have 22.6%, right? How much of this 22 is coming from the clusteration, and how much was coming from the actual solving of optimization problem?
For that, I need if I open another PDF file, are you going to see it? Your question was how much time is coming from the clustering, from the KNN?
Yeah, because I was just curious, because
the learning part of the algorithm is super fast.
Okay, all right.
Because we do it in parallel, so you don't have to. We do it in parallel for all lines.
Okay.
So it takes nothing.
All right. And my last question is about the first part, actually. So you chose the 672 length of the data set, right? So does your proposed method performance vary depending on your choice of length of data? For example, if you choose a, say, larger size of the data, for example, if you consider, say, 60 days, and then your length of data will be doubled, right? In that case, probably representative days-based approach can be more accurate than your.
Oh, that's in the figure here. That's on the left figure.
Okay.
Yeah, I probably I didn't spend enough time on this slide. So this is the on the x-axis. What you have is the number of period that you choose. So 60 days. That's like 1,000 and something. So that's probably this here.
Oh, I see. All right, I missed that. Thank you so much for
Yeah.
answering.
So this so it's the so the red dots are our proposed methods, and it becomes better than the other for all range of periods that you choose.
Okay, so the next question comes from Robert. Robert, please go ahead.
Hi.
Hi.
Thank you, Salva, for your talk. I am especially interested in the second part of the methods you showed. And actually, Jip already asked one of my questions, depending on the time, but I have a quick follow-up. So if I understood correctly, the time you reported includes the process time of the algorithm that you included, plus the optimization of the actual problem, right?
Yes.
So it's a single time step. And have you tried or have you looked into additional gains from the different methods if you basically process the network constraints before and then apply it to multiple time steps to gain additional basically value from processing at once?
I'm not sure I understand. You mean if the hours are similar enough, so I don't have to repeat the learning.
Okay, so for the other methods, for example, it could be I don't know. For example, the method you call rolled method.
Yes.
Like you could try and find, like you could have a data set of, I don't know, a couple of time steps and process the method with that, and then have the optimization running for multiple time steps, so that basically the ratio of process time to solving a time step of the unit commitment gets better. Do you know what I mean?
Not sure, because for example, roll method, you only solve for each line. You have to solve an optimization problem, just one in your life, let's say. So it's not like, and then if it's impossible that a line get congested, even though all generators are pushing forward to congest that line, then to just remove that constraint safely for the rest of your life, let's say. So in that case, you don't have to do it. I don't know if that's related to your question.
Okay. No. I think I think it makes sense. Okay, but my next question would be: have you also tried extending this to contingency scenarios?
No, not yet. But that was a point raised by reviewers.
Okay.
That's future work.
Okay.
Yeah.
Okay. Thank you.
Thank you, Robert.
Thank you so much, Robert. I don't see any other questions, so I think I'll give a few more. Oh, no, we have one question from Jose Cordova Garcia. Jose, please go unmute yourself and.
Hi.
Hi.
Thanks for the presentation. So I have a couple of questions just to make a point a little bit more clear on the second part of your presentation. The last method you're showing, the DD plus CG, is the method you have to use whenever the data-driven said a line was not congested, but it actually is. So you have to include it in the optimization problem. Is that right?
Well, it depends on your on how picky you are, etc. So in the purely data-driven method, the infeasibilities that we obtain in the simulations are very low. So, for example, in the real size case study, it's only 0.03%. And that's I mean, I wouldn't worry too much about these infeasibilities in real life, because I mean, you have frequency control, you have a lot of options to adjust these small infeasibilities between generation and demand, right?
Yes.
So so that's good enough. But let's say you are super picky and you say, well, no, I don't, even though the feasibilities are very small, I don't trust my frequency control, my automatic generation control. I want a commitment that is 100% feasible. Then in that case, you use the constraint generation method.
Gotcha. Okay. Have you measured it? Like how many times you reach an feasibility?
Yeah, that's the 0.03%.
Okay, gotcha.
Yeah,
Okay.
so that's like I mean, it's a little bit. I mean, in the paper you can find a little bit more details. Here it's a little bit more like, you know, like
Oh,
general
I see.
message, but it's like you are. Yeah, it's like somehow like it's the value of the slacks variables compared to the total demand throughout all the days.
Okay. Okay. And
Yeah.
if you allow me, I have like just a detail on the method you use for classifying this congestion on the lines or not. How many time periods you're actually considering?
For training, you mean?
And not the, like to determine a neighbor, right? You consider.
Yes. So in the paper we changed that. So the number of neighbors, I guess you're meaning, right? So how many neighbors we use?
Yes.
Yeah. So in the paper we changed that. So and this is related to Jeep question. So if you increase, as you increase the number of neighbors, you become more and more conservative, right? And then in the paper you can see how the number of neighbors affect the results. But basically you are like you remove less constraints because you are more conservative. Then the time is a little bit higher, but you are these infeasibilities you were talking about are also reduced. It's not guaranteed that they are going to zero, but they are reduced.
Okay, Mark, thank you.
Yeah, thank you.
And we have a question which was sent to the chat. So can you please, Salva, comment if your unit commitment model considers any dynamic interactions with the system? If so, which one have you particularly paid attention to, or which one you think are the most important?
What dynamic what?
Dynamic interactions within the system. I think the person refers to stability constraints, synchronizations constraints.
Okay, no, I mean, as you saw, we didn't, because I mean, at some point we included like intertemporal constraints like ramping or minimum times, and things got a little bit nasty. So this still we are still doing research on how to include more intertemporal constraints and make things work.
Okay.
I'm not sure if that's answering, but I hope so.
It gives a perspective because in the question it was not phrased exactly. So I think it was open to our interpretation of what dynamic interactions are. In any case, I don't see any more raised hands. I think it's a good sign. It means that the presentation was clear and sparked some interest in follow-up discussions. So thank you so much, Salva.
Thank you
We're sending
for
a
the
bunch
invitation.
of claps to you, and hopefully eventually you're gonna come back to campus and we will have
I hope so.
We'll have a chance to have a real life experience. And thank you all for attending the seminar. Yeah.
Okay, thank you.
Bye bye.